In the 48 hours surrounding the closest approach of 3I Atlas to Earth, something unusual appeared in the X-ray data. Not an increase in light, but a disappearance. The problem is not what 3I Atlas was emitting. The problem is what it was blocking. If an interstellar object can interact with high-energy radiation, then the real question is no longer what it is, but how it is physically structured. In astrophysics, X-rays are not mysterious beams or exotic signals. They are a natural form of high-energy radiation, produced when extremely hot plasma interacts with magnetic fields or streams of charged particles moving at high velocity. Because of this, X-rays are usually a sign of violence in space. Shock fronts, stellar winds, magnetic reconnection, and energetic particle exchange all leave X-ray fingerprints behind. When scientists use the phrase X-ray shield, they are not describing a solid wall or an engineered barrier. In scientific terms, it refers to a region where X-ray intensity is measurably reduced as radiation passes through matter, plasma, or a structured electromagnetic environment. These attenuation zones are not hypothetical. They have been observed before, especially around plasma-rich comets and within the magnetospheres of planets, where charged particles and magnetic fields reshape how high-energy radiation propagates. What makes 3I Atlas unusual is not the existence of attenuation itself, but its scale and context. This is a relatively small interstellar object, not a planet and not a star. Yet the X-ray behavior around it does not match simple comet models. That mismatch forces a deeper question. If this is not a physical shield, and not an artifact of the instruments, then what kind of physical mechanism could produce the same effect? The X-ray data linked to 3I Atlas does not come from a direct image of the object itself. There is no glowing halo and no sharp X-ray outline captured by a telescope. Instead, the signal emerges from how the background X-ray field behaves as the object moves through space. Astronomers monitor distant X-ray sources and measure how their intensity changes before, during, and after 3I Atlas crosses the same line of sight. When high-energy radiation fades in a localized region and then returns to normal, something along that path must have interacted with it. This method is not speculative. It is a standard technique in astrophysics, used to study planetary atmospheres, cometary comas, and diffuse gas between stars. The physics is straightforward. X-rays do not simply vanish. They are either scattered, absorbed, or redistributed by matter, plasma, or electromagnetic structures. What makes this case unusual is not the method, but the consistency of the effect tied specifically to the presence of 3I Atlas. JAXA and several research groups across Asia pay close attention to X-ray behavior when observing comets for a clear reason. Cometary X-ray emission is typically weak and well understood. It arises mainly from charge exchange between the solar wind and neutral gases released from a comet's surface. As a comet approaches the Sun, this interaction usually becomes stronger. The closer the comet gets, the more X-ray activity models predict. 3I Atlas did not follow that pattern. instead of showing enhanced X-ray emission near closest approach. The data revealed a stable region where X-ray intensity was suppressed as the object passed through. This suppression was not chaotic, fleeting, or inconsistent. It persisted across multiple observations and independent datasets. That stability is what made the result impossible to dismiss as noise or calibration error. This is why the phrase "didn't expect this" matters. Not because it hints at hidden technology, but because it signals a breakdown in familiar models. The behavior does not fit comfortably within what decades of solar system comet observations would predict. Something about 3I Atlas is interacting with high-energy radiation in a way that standard assumptions do not fully explain. If Atlas does not behave like a typical solar system comet, then where exactly does its physical composition differ? Once the X-ray anomaly is treated as a physical effect rather than a signal of technology, the problem shifts from speculation to structure. Several natural mechanisms can plausibly produce X-ray attenuation without invoking anything artificial. One possibility is an unusually dense plasma region surrounding the nucleus. If 3I Atlas releases volatile material in a way that traps charged particles, that plasma cloud could scatter or absorb high-energy radiation passing through it. A second explanation involves temporary magnetic interactions between Atlas and the solar wind. Even a weak or transient magnetic field can reorganize charged particles around an object, creating a structured environment that alters how X-rays propagate. A third candidate is a cloud of ultrafine dust. Extremely small grains are surprisingly effective at absorbing high-energy radiation, especially when distributed over a large volume. Such dust would not reflect much visible light, but it could quietly suppress X-rays. These explanations gain strength when viewed alongside other observed behaviors. 3I Atlas shows non-gravitational acceleration, suggesting ongoing interaction with its environment rather than passive motion. Its activity also intensifies after perihelion, not before, which runs counter to simple heating-driven models and points toward deeper structural processes. Most importantly, the X-ray anomaly does not exist in isolation. It aligns with the observed color changes in the coma, the presence of an anti-tail, and an unusually low reflectivity that makes the object darker than expected. When multiple anomalies point in the same direction, where is the boundary between a rare natural phenomenon and a structure we have never encountered before? Interstellar objects are uniquely positioned to create what feels like technological behavior because they are not products of our solar system. They form around different stars, under different chemical ratios, and within radiation environments that may be far harsher or more chaotic than anything our local models are tuned for. By the time such an object enters our system, it already carries a physical history we have never calibrated against. When that object encounters the solar system for the first time, it is suddenly immersed in a new regime. The solar wind, the sun's magnetic field, and intense thermal gradients all act on materials that did not evolve here. Interactions that are rare or weak for native comets can become amplified, producing behaviors that look organized, directional, or intentional simply because the physics is unfamiliar. Human perception plays a critical role in how these effects are interpreted. The brain is exceptionally good at detecting patterns, and it is especially sensitive to regular motion. Symmetry, and stability. When a natural process produces ordered behavior, we instinctively assign purpose to it. In situations where data is limited, that gap is often filled with technological language because it feels intuitive and familiar. This is precisely why science is cautious. An anomaly does not automatically imply something artificial. A deviation from expectations is not the same as evidence of design. The discipline of astrophysics is built around resisting early conclusions and separating what is unusual from what is engineered. Even when the distinction feels emotionally compelling. If we do not yet fully understand interstellar physics, then are we too quick to project human technological language onto the natural behavior of the universe? As 3I Atlas moves away from the inner solar system, it takes something with it that cannot be recovered. The specific data gathered during this brief passage, the transient interactions with solar radiation, plasma, and magnetic fields, and the physical configuration it displayed at that moment will never appear in exactly the same way again. This encounter was a one-time experiment conducted by nature itself. What remains is not the object, but the consequences. Existing models of interstellar bodies will need revision. Not because they were careless, but because they were built on assumptions drawn almost entirely from solar system material. Observations of X-ray behavior around interstellar objects are likely to become a priority rather than a niche curiosity. Because Atlas demonstrated that high-energy interactions may be one of the most sensitive probes of their true nature. The most important legacy of 3I Atlas is not a definitive label. It is not the answer to whether the object was ordinary or extraordinary. Its real value lies in the fact that it opened a new layer of physics for investigation. One that sits at the boundary between stellar environments and planetary systems, where our intuition is weakest and our models are least tested. Science does not advance by chasing sensational conclusions. It advances by asking questions that survive contact with data. And Atlas has given us one of those questions. Quietly and without spectacle, when the next interstellar object appears, will we look at it with the same assumptions we carried before? Or will we finally be ready to listen to what the data is actually telling us?